The world first started seeing spectacular images of the cosmos that were captured by the powerful James Webb Telescope.
The James Webb Telescope might have just disproved the Big Bang theory. Cosmology took a giant leap when the James Webb Space Telescope launched on Christmas Day in 2021. Since then, it has surpassed astronomers' wildest expectations, making astonishing discoveries that challenge our deep-rooted beliefs. What are the cosmic mysteries this new telescope is revealing? What is the fate of the universe we live in? Join us as we unravel the old structures and galaxies the James Webb Telescope just detected. As we journey back over 13 billion years, we catch a glimpse of a young universe, a spectacular creation believed by most scientists to have begun with the Big Bang. This theory explains how everything, from stars to planets and life on those planets like us, might have come into existence. There are other theories surrounding the universe's origin, though. The steady-state universe, for one, proposes a perpetually expanding universe, maintaining constant density over time, leading to continual renewal, where old astronomical objects become outworn as new ones take their place. Another theory, the bouncing cosmology or Big Bounce model, suggests a cyclical universe, shrinking and expanding in successive cycles. Moreover, the plasma or electric universe model states that plasma, the fourth state of matter, plays a pivotal role in cosmological events. This theory revolves around electric currents flowing through plasma filaments, influencing the formation and behavior of galaxies, stars, and planets. Among all these, the most popular and widely accepted theory among scientists and the general public is the Big Bang theory. However, despite its popularity, new and better data has been nudging against some predictions of this famous theory. NASA's James Webb Space Telescope, a $10 billion marvel designed to unveil the universe's secrets, was introduced to get the data. This is the Hubble's grand successor, a telescope with unparalleled vision. After just a year in space, the James Webb Telescope is astonishing scientists. Its unparalleled gaze into the cosmos has unveiled galaxies so ancient that they might challenge what we thought we knew about the universe's origins. The astronomer, Rohan Naidu, was sitting at home one day, sifting through data from the James Webb Telescope with his algorithm. Suddenly, he stumbled upon something groundbreaking. He found a galaxy dating back a mere 300 million years after the Big Bang, older than any galaxy ever seen before. This new galaxy, nicknamed Glass Z13, caused a worldwide stir. It was a moment beyond astronomers' wildest dreams. The James Webb Telescope, stationed far from earthly interference and chilled close to absolute zero, was built to crack open the secrets of cosmic dawn. And the era, just a few hundred million years post-Big Bang, is a cosmic puzzle waiting to be solved. With its sophisticated instruments, the telescope aims to unravel the mysteries of how the first stars and galaxies formed. By studying these ancient galaxies, scientists hope to confirm their models or discover new frontiers of understanding. This exploration might reveal unseen aspects of dark matter, dark energy, and the complex interplay between starlight, gas, and dust, leading us to profound discoveries. So, what new discoveries have scientists uncovered with JWST? How does it change our belief in the Big Bang? Let's delve into the fascinating details together. Initially, scientists thought these observations would take a while to materialize. They figured the first galaxies would be small and hard to spot, maybe just a few interestingly distant ones in the pilot scans of the James Webb Space Telescope, or JWST. But the plan went off script right away. As soon as the telescope's scientists shared the very first images of the distant universe, astronomers like Naidu at MIT began uncovering countless galaxies within them. These galaxies were older, larger, and brighter than anyone had predicted. It was like a discovery race every day, with new claims surfacing about breaking records for the earliest known galaxies. The surprise was real. Charlotte Mason, an astrophysicist at the University of Copenhagen, said everyone was freaking out with the discoveries. This unexpected revelation sent theorists and observers into a frenzy. They scrambled to make sense of it all. Were these unusually mature early galaxies real, or a result of flaws in analyzing the telescope's initial observations? Or could they fit into our standard understanding of the universe? These findings aren't just about galaxies, though. They challenge our fundamental grasp of the cosmos. The stakes are high, as the revelations might rewrite the beginning chapters of cosmic history, which not only involve distant eras and galaxies, but also our existence here in our familiar Milky Way. Mark Makarian, a JWST scientist, put it vividly that these machines are built not to confirm the paradigm but to break it, and that might just be what it's doing. The aim was never to stay within our comfort zone of understanding, but to push boundaries and possibly shatter the established theories. The observations made by JWST about these early galaxies have been brewing for billions of years, tracing back to the Space Telescope Science Institute, STSCI, in 1985. Back then, the Hubble Space Telescope was at its peak, and while its potential was exciting, astronomers like Garth Illingworth, then deputy director of STSCI, were already thinking ahead. Riccardo Giacconi, the director at that time, urged them to consider what would come after Hubble, even though it seemed too early to think about it. This visionary approach set the wheels in motion for what eventually became the JWST, named after a former NASA administrator. The Hubble telescope, amazing as it was, had limitations. It could only observe visible light, making it blind to the distant galaxies whose light had shifted into the infrared spectrum due to the expansion of the universe in a phenomenon known as redshift. JWST, on the other hand, was designed specifically for this purpose. It's like the upgraded version with infrared vision, equipped with a massive mirror that could capture light from these far-off early galaxies. Its primary mirror is a whopping 6.5 meters in diameter, made up of 18 hexagonal segments of beryllium coated with gold. That's 7 times larger than the Hubble Space Telescope's mirror, allowing the JWST to gather more light and observe incredibly faint celestial objects. The JWST is also shielded by a sun shield the size of a tennis court, consisting of 5 layers of ultra-thin membrane material. This shield acts as a protective barrier against the intense heat and radiation emitted by the sun, Earth, and Moon. It creates an environment for the telescope that's not just cool, but also stable enough for its instruments to function optimally. Speaking of temperature, the sun shield works wonders. It reduces the temperature from a scorching 383 Kelvin or 231 Fahrenheit on the sun-facing side to a shocking cold 36 Kelvin, about minus 394 Fahrenheit, on the telescope-facing side. The JWST boasts a focal length of 131.4 meters, enabling it to capture incredibly detailed images with an optical resolution of about 0.1 arcseconds. In terms of its overall mass, it weighs approximately 6,500 kilograms. The need for this new telescope was cemented in 1995, when astronomers pointed Hubble at what appeared to be an empty patch of the sky for 10 days. What they captured, known as the Hubble Deep Field, was mind-blowing. They found thousands of galaxies, stretching back as far as 12 billion years into the universe's 13.8 billion-year history. These galaxies were all over the place. As Garth Illingworth, now an astrophysicist at the University of California, Santa Cruz, observed, the Hubble Deep Field gave us a spectacular view, revealing that the early universe was even busier and more thrilling than anticipated. It was a grand view for those who took the time to look carefully. As remarkable as the Hubble Deep Field was, astronomers hungered for more. After over 2 decades of hard work and a hefty price tag of about $10 billion, the James Webb Space Telescope finally launched on Christmas Day in 2021. A month later, it reached its deep space destination, undergoing thorough testing to ensure optimal performance. By July 2022, it was ready to embark on its much-anticipated first year of science observations, known as Cycle 1. The initial focus of the telescope's observations included high-impact programs across various disciplines. 2 notable ones were the Cosmic Evolution Early Release Science Survey, SEERS, and the GRISM Lens Amplified Survey from Space Glass. These surveys independently invested dozens of hours scouring the sky for galaxies in the early universe. Notably, their expectations weren't extravagant. They were hoping to find something a bit more detailed than the Hubble Deep Field. However, to the surprise of astronomers, extremely distant galaxies made an early entrance into the scene. The University of Texas at Austin's Stephen Finkelstein, leading the SEERS program, noted that the anticipation was for extremely distant galaxies to surface after a few cycles of data from multiple programs. But right from the get-go, these galaxies made their presence known. Hubble's previous record holder for the most distant known galaxy was GNZ 11, identified in 2015 at a redshift of 11. This redshift corresponds to a cosmic age of around 400 million years, a time when galaxy formation was presumed to commence. However, the initial data from GLASS revealed something even more astonishing. Teams, led by researchers like Naidu, independently stumbled upon GLASS Z13 at a redshift of 13, about 70 million years further back in time. In their quest for speedy results, researchers used redshift estimates derived from brightness-based measurements, which, though less precise than direct measurements, hinted at a galaxy unexpectedly bright and huge. The simplified technique indicated that GLASS Z13 was already home to a mass of stars equivalent to 1 billion suns, just a few hundred times less than the stellar population of our Milky Way. This revelation challenged existing expectations and underscored the groundbreaking potential of the James Webb Telescope. But this record-breaking discovery didn't hold the spotlight for long. In the days that followed, a multitude of galaxy candidates from SEERS and GLASS emerged, boasting estimated redshifts as high as 20, which is just 180 million years after the Big Bang. What's even more mind-blowing is the structure of some of these galaxies. They have disk-like formations that weren't expected to manifest so early in cosmic history. Galaxies resembling our Milky Way were popping up at a redshift of 10, less than 500 million years after the Big Bang. These grand entities appearing so swiftly challenge the predictions made by the standard model of the universe's evolution, known as lambda cold dark matter (LCDM). This model is the best shot scientists have for understanding the properties of dark energy, lambda, and dark matter (CDM), which together dominate the formation of large-scale cosmic structures. The emergence of these massive galaxies contradicts the slow and orderly process anticipated by the model. Michael Boylan Colchin, a cosmologist at the University of Texas at Austin, explains that even if you had all the ingredients needed to form stars and clicked your fingers in an instant, you still wouldn't get galaxies that big that early. To grasp this, let's rewind to the early moments post-Big Bang. In the first second, the universe was a scorching soup of primordial particles. Fast forward around 400,000 years, and the universe was finally cool enough for atoms to form. About 100 million years later, conditions seemed ripe for the birth of the first stars. They were huge balls of hydrogen and helium with distinct properties due to the absence of heavier elements found in modern stars. These early stars grouped into proto-galaxies, hanging onto massive, invisible scaffolds of dark matter. Gravity caused them to interact, leading to mergers that eventually birthed larger galaxies. This process, from chaos to the more orderly universe we know, is thought to have taken roughly 1 billion years. While there's significant confidence in understanding events after the Big Bang, unraveling what transpired before this monumental event remains a profound mystery that scientists continue to explore and theorize about. And now, the James Webb Telescope's discovery challenges the narrative of what happens after. So, what do we actually believe? Instead of observing many small proto-galactic fragments yet to merge into larger galaxies, researchers are seeing already huge galaxies from such a long time ago. Stacy McGaugh, a cosmologist at Case Western Reserve University, notes an unexpected observation, though. She noted that some of these might even be masquerading as distant galaxies due to dust, making them appear fainter and farther than they are when measured based on brightness. Follow-up observations of GLASS Z13 using the Atacama Large Millimeter Array, ALMA, in Chile provided interesting insights. It suggested that the galaxy might not be one of those imposters, as ALMA didn't detect significant dust. However, ALMA's struggle to see the galaxy shows the challenge telescopes face in confirming observations made using the James Webb Telescope's advanced capabilities. One controversial idea floating around is the modified Newtonian dynamics, MOND, which shakes up the notion of dark matter's existence. MOND proposes that the effects attributed to dark matter could actually be fluctuations in gravity on a large scale. Some scientists, like McCaw, one of its supporters, believe that JWST's observations might align with this theory. However, others, like Taipei, remain skeptical about MOND's ability to explain everything. Another simple explanation proposed is the absence or minimal presence of dust in early galaxies. This could make these galaxies appear brighter than expected, throwing off calculations of their true masses. Ferrara suggested scenarios where dust might not have had enough time to form or got expelled during the initial phases of galaxy formation. Mason and her colleagues offered an alternative viewpoint, suggesting that JWST might only be observing the very brightest young galaxies. This theory speculates that certain galaxies are more predisposed to form stars in the early universe, making them easier to spot. Spergel, a theoretical astrophysicist, proposed that magnetic fields might have played a significant role in kickstarting star formation early in the universe's history. This, combined with higher gas pressures and temperatures, could have created an environment conducive to rapid star formation. The swamp of scientific papers from JWST's initial observations didn't happen by chance. When the first data arrived, astronomers were ready and waiting. Instead of traditional peer-reviewed publishing, they shared their findings on sites like Arxiv, enabling real-time discussions on platforms like Twitter. This rapid exchange of ideas and findings led to intense scientific scrutiny and debate. But, as always, caution is key. Calibration issues with JWST might have affected some results, leading to potential recalibrations of data. Adams and his colleagues found a significant redshift change in one galaxy, highlighting the need to tread carefully before jumping to conclusions. While these recalibrations might not nullify all the high redshift galaxies observed by JWST, their sheer number implies that the early universe might be far more different than we previously assumed. These surprises emphasize that the universe loves to challenge our theories, reminding us that there's still so much we have yet to uncover. Stephen Finkelstein, emphasizing the slim odds of us all being wrong, hinted at the urgency among astronomers to conduct follow-up observations using the JWST. There have also been a dozen proposals from various groups, all vying for additional JWST observing time. Most of these proposals aim to closely scrutinize high redshift galaxy candidates, seeking to confirm these early discoveries. Treyu, who proposed one of these projects, mentioned the importance of confirming these discoveries given the excitement they've stirred up. Notably, the proposals are just the beginning. There's a whole lineup of programs geared towards hunting distant galaxies. The Cosmos Webb project, led by Cartel Tepe, plans to search a broader stretch of the sky for hundreds of hours, estimating the detection of thousands of these early galaxies. This project aims to significantly expand our knowledge of early galaxies, but the search doesn't end there. Other projects aim to seek evidence of the universe's first proto-galaxies. They're hunting for clues, perhaps in the explosive deaths of massive early stars or the dazzling displays of supernovae, serving as markers for these ancient celestial formations. Some estimations even speculate that JWST could peer as far as a redshift of 26, a mere 120 million years after the Big Bang. They also hope to discover what came before the Big Bang. That's where things get murkier. The cosmic dark ages cloaked the universe in a hydrogen fog, obstructing the light of the first stars and galaxies, making it nearly impossible to see beyond that time. Even before stars formed, the universe was predominantly dark, with dark matter, which doesn't emit light, dominating. This dark age presents a barrier to peering deeper into the universe's origins. However, Stephen Hawking has theories that stretch the limits of our understanding of the universe. His predictions about humanity's remaining time on Earth and Earth's fiery future aside, Hawking delved into the mysterious period preceding the Big Bang, painting an extraordinary picture of the cosmos's birth. Hawking's proposition, the no-boundary proposal, outlined alongside collaborator James Hartle in 1983, envisioned the universe's shape resembling a shuttlecock. This concept visualizes a cosmos that smoothly expanded from a point of zero size, like a shuttlecock's bottom, gradually widening upwards. They formulated a wave function of the universe that encloses its entire past, present, and future in a single description, eradicating the need to contemplate creation seeds, a creator, or a time before the Big Bang. In this model, time takes on a revolutionary role. Instead of an evolving series of moments, each moment represents a cross-section of the shuttlecock-shaped universe. Time becomes a correlation between the universe's size in each section and its properties, particularly entropy, which increases from the cork to the feathers, depicting an emergent arrow of time. Hawking elaborated that events before the Big Bang are indeterminable since they hold no observable consequences, suggesting the erasure of such events from the theory, effectively proposing that time initiated at the Big Bang itself. He likened the universe's structure to the Earth's surface, emphasizing the notion that there was nothing around before the Big Bang. Hawking's new approach, influenced by physicist Richard Feynman's methods, utilized a wave function derived from Feynman's quantum mechanical calculations. Later in his life, he explored holography, treating space-time as a hologram, attempting to understand the wave function more comprehensively. His collaborations continued even in his absence, with scientists like Neil Turok and colleagues investigating cosmological models that echo Hawking's no-boundary proposal, envisioning a universe with sections resembling an hourglass, reflecting CPT symmetry. Yet these models are still being speculated, particularly in comprehending the singularity where sections meet. This exploration of the pre-Big Bang era by Hawking remains a captivating subject, stimulating physicists' curiosity and inspiring ongoing research into the mysteries of our universe. Interestingly, another theory posits that the Big Bang wasn't the start of everything, but a shift from a contraction phase to an expansion phase. This notion implies that there is a cyclical pattern of infinite Big Bangs, where the universe expands, contracts, and expands again. In essence, the widely accepted Big Bang theory proposes that the universe commenced from an immensely hot and dense singular point, inflating at unimaginable speeds before gradually expanding over billions of years. However, we have seen recent findings from the James Webb Space Telescope cause a wave of skepticism among some scientists. Eric Lerner and Ricardo Scarpa propose a non-expanding universe, supported by their analysis of galaxies' redshifts, which doesn't align with the anticipated expansion theory. They argue that the JWST images reveal unexpectedly smooth and organized galaxies, disrupting the prevalent notion of galaxies formed through collisions and mergers. Moreover, observations of galaxies with stellar populations significantly older than predicted by the Big Bang theory have led some scientists to question its validity. According to these skeptics, the existence of these galaxies challenges the idea that nothing existed before the Big Bang. Despite these contradictions, advocates of the Big Bang theory argue that these new revelations don't entirely discredit the theory. The theory relies on three key elements: the redshift of distant galaxies, the cosmic microwave background radiation, and the relative abundance of elements in the early universe. These pillars have formed the basis of the standard model of cosmology, explaining various cosmic phenomena. While the JWST's findings seem perplexing, experts believe they might offer a deeper understanding of our universe. They emphasize that the telescope's observations challenge some assumptions about the Big Bang theory, but don't unequivocally disprove it, and that's why they're undertaking these new projects. The revelations signify the ongoing evolution of our understanding of the cosmos, prompting scientists to reassess certain concepts while not entirely dismissing the established theories. The focus of these projects isn't solely on discovery, though. It's about confirmation, too. Even confirming a handful of these high redshift galaxies would be an incredible feat. Naidu expresses the significance, saying it would affirm that we're not being misled by these findings. The James Webb Telescope has sparked a new wave of scientific exploration. Despite uncertainties, the rapid sharing of new discoveries has ignited a spark within the astronomical community. Treyu echoes this sentiment, describing the engagement and excitement among astronomers as fantastic. It's a thrilling time to be exploring the cosmos, peering into the unknown. Thanks for watching. Check out another of our interesting videos by clicking on the link appearing on your screen right now. Also, subscribe to the channel for more intriguing videos, and we'll see you soon.